In 1981, I attended a cosmology conference at the Vatican, organized by the Jesuits, which I found rather amusing. The Catholic Church assembling the world's leading physicists to discuss the origin of the universe. I presented a paper at that conference proposing that the universe might have no boundary and no beginning. Afterward, we were granted an audience with the Pope, and he told us it was quite acceptable to study the evolution of the universe after the Big Bang, but that we should not inquire into the Big Bang itself because that was the moment of creation, and that was the work of God. I was glad he did not know the subject of the paper I had just given, because what I had argued, and what I still believe the mathematics shows, is that there was no moment of creation to inquire into. That tends to get people's attention. The question I hear more than almost any other is what happened before the Big Bang. It seems perfectly reasonable, because everything has a cause, and every event has something that came before it. You were born because your parents met. The Earth exists because a cloud of gas collapsed under gravity 4.5 billion years ago, and the Big Bang happened, which raises the obvious question of what lit the fuse, and what was there 1 second before everything began. I spent the better part of my career pursuing this question, from my early work on singularity theorems at Cambridge, through decades of research into quantum cosmology and quantum gravity. And I arrived at an answer that disturbs people, not because it is complicated, though the mathematics behind it is considerable, but because it dismantles the question itself. The answer is not some exotic event that preceded the Big Bang. Time itself began, and asking what came before the Big Bang is like asking what is north of the North Pole. You can stand at the North Pole and point in any direction, and every direction you point is south. There is nothing north of it, not because something mysterious is hiding there, but because the concept has no meaning. Think about what that implies. This is not a dodge, and it is not me saying we do not know yet. It is a precise statement about the geometry of the universe, and it took the combined efforts of general relativity, quantum mechanics, and entirely new mathematics to arrive at it. Let me walk you through how we got there, because the story itself reveals something extraordinary about how physics works. In 1915, Einstein published his general theory of relativity, and what he showed was that gravity is not a force pulling objects together across empty space, which was the picture Newton gave us. Gravity is the curvature of space-time caused by mass and energy. The Earth does not pull you down, because what actually happens is the mass of the Earth warps the geometry of space and time around it, and you follow a curved path through that warped geometry. It was a revolution in our understanding of the universe, and it carried a consequence that Einstein himself found deeply troubling. His field equations, when applied to the universe as a whole, to all the matter and energy everywhere, showed that the universe cannot be static. It must be either expanding or contracting, and Einstein found this so disturbing that he introduced a fudge factor, the cosmological constant, to hold the universe still. He later called it the greatest blunder of his career, because the evidence was already emerging. A Belgian priest and physicist named Georges Lemaître had independently shown from Einstein's own equations that the universe should be expanding, and that tracing that expansion backward leads to what he poetically called the primeval atom, a single point from which everything erupted. Then, in the late 1920s, Edwin Hubble, working at the Mount Wilson Observatory in California, confirmed it through his telescope. The galaxies are all receding from us, and the farther away they are, the faster they move. Lemaître was right, and Einstein was wrong. Running that expansion backward makes everything converge. The galaxies crowd together, the density climbs, the temperature soars, and going back far enough, you reach a point of infinite density and infinite curvature of space-time, a singularity, the beginning. But here's the thing most people never hear about. In the 1960s, Roger Penrose, who would decades later receive the Nobel Prize in Physics for this work, proved a remarkable theorem about black holes. He showed that under general relativity, a collapsing star must produce a singularity, a point where the curvature of space-time becomes infinite, and the known laws of physics break down. I was a young research student at Cambridge at the time, working under Dennis Sciama, 23 years old, recently diagnosed with motor neuron disease, and given roughly 2 years to live. I needed a thesis topic, and when I saw what Penrose had done for black holes, I realized the same mathematics could be applied in reverse, not to a collapsing star, but to the expanding universe. That became my doctoral work. Together, Penrose and I proved a series of singularity theorems showing that if general relativity is correct, and if the universe contains the amount of matter we observe, a singularity in the past is not merely possible but inevitable. The universe must have emerged from a state of infinite density, and our theorems carried an uncomfortable implication that general relativity predicts its own breakdown. At the singularity, the equations give infinite answers, and the theory ceases to function at the very point that matters most, the origin of everything. This bothered me enormously, not as a philosophical nuisance, but as a signal. A theory that predicts its own failure is telling you something important, that you need a better theory. And that better theory, I became convinced, had to combine the two great frameworks of 20th century physics, general relativity, which governs the very large, stars, galaxies, the architecture of the cosmos, and quantum mechanics, the physics of the very small, pioneered by Bohr, Heisenberg, Dirac, and others, which governs atoms, particles, and the fundamental forces. Both theories are spectacularly successful in their own domains, and they are fundamentally incompatible. At the singularity, you have something that is both infinitely small and infinitely massive, meaning you need both theories simultaneously, and they refuse to cooperate. The search for a consistent theory that unifies them, what physicists call quantum gravity, has been the great unsolved problem of theoretical physics for nearly a century. But even without a complete theory, there are things we can calculate, and what I found, using a particular mathematical approach, shattered the question of before. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey, trying to calibrate a large microwave antenna, and they kept picking up a faint background hiss that they could not eliminate. They checked for equipment faults, even cleaned pigeon droppings from the antenna, and the hiss persisted. It came from every direction in the sky, uniformly, and what they had accidentally detected was the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, cooled over 14 billion years to a temperature just 2.7 degrees above absolute zero. This was not theory. This was the Big Bang made observable and measurable. Later missions, the COBE satellite, the WMAP satellite, and most recently the Planck Space Observatory, mapped this radiation with extraordinary precision, confirming the predictions of Big Bang cosmology down to the minute fluctuations that seeded the formation of galaxies. The evidence is overwhelming that the Big Bang happened. The question that remains is what was its nature, and whether physics can describe it without breaking down. And this is where it gets strange. In quantum mechanics, there is a mathematical technique involving what is called imaginary time. Imaginary is an unfortunate name because it suggests something fictional, but it is not. Imaginary numbers are a rigorous mathematical tool, the square root of -1. Your mobile phone uses imaginary numbers every time it processes a signal, and electrical engineers work with them daily. The mathematics that underpins the origin of the universe is the same mathematics that lets you make a telephone call, and that should tell you something about the deep unity of physical law. When you replace ordinary time, what physicists call real time, the kind you experience and measure with clocks, with imaginary time in the equations of general relativity, something remarkable happens. The distinction between time and space disappears. Let me say that again, because it is the key to everything that follows. In imaginary time, time becomes indistinguishable from space, turning into just another dimension, like left-right, forward-backward, up-down, and this transforms the geometry of the universe in a way that changes all of our conclusions. In real time, the history of the universe has a singularity, a point where the laws of physics cannot be defined, a boundary and an edge. But in imaginary time, there is no singularity, and the universe becomes smooth, finite, and without any boundary at all, curving back on itself like the surface of a sphere. This is the no-boundary proposal. I developed it with James Hartle of the University of California, Santa Barbara, and we published it in 1983, 2 years after that Vatican conference where I first floated the idea in front of the Pope. The proposal uses an approach called the sum over histories, an idea originally developed by Richard Feynman. In quantum mechanics, a particle does not follow a single path from one point to another, and instead you must consider every possible path simultaneously, weighted by its probability. Feynman showed that you sum over all possible histories to calculate what actually happens, and Hartle and I applied this framework to the universe itself. We asked what happens if you sum over all possible histories of the universe, in imaginary time, with no boundary condition. The answer was electrifying. The most probable histories, the ones that contribute most to the sum, look like the universe we actually observe, expanding, cooling, forming structure, allowing complexity to emerge. Picture the surface of the Earth. It is finite, with a definite area, but it has no edge. You can walk in any direction and never fall off, And you never reach a point where the surface ends because the geometry closes back on itself. The no-boundary proposal says the universe, in imaginary time, behaves exactly like this. It is finite in extent but has no boundary, no edge, no beginning point. The Big Bang is not a sharp point, not a singularity, and not an edge. It is more like the south pole of the Earth. As you move south, as you go back in imaginary time, the circles of latitude get smaller and smaller, just as the universe gets smaller and smaller. At the South Pole, everything converges to a single point, but it is not a boundary or an edge, just a perfectly regular, smooth point of the geometry, no different from any other point on the surface. There is nothing south of the South Pole, not because of some wall or some limit to your knowledge, but because the direction south simply ceases to exist there. The universe, on this account, did not emerge from anything and did not require a cause. It is self-contained and complete. The laws of physics, applied correctly using quantum mechanics and general relativity together, describe a universe that has no boundary, no edge, and no moment of creation that requires something outside of physics to explain. I know what you're thinking, that imaginary time sounds like a mathematical trick, and you want to know which description is real, imaginary time or ordinary time. I have thought about this a great deal. I am what philosophers would call a positivist, meaning a physical theory is a mathematical model, and if the model describes the observations, you cannot meaningfully ask whether it is real. It is useful, it works, and that is all science can say. In imaginary time, the universe has no singularity, no boundary, no beginning. In real time, it does. Both are mathematical descriptions, but the imaginary time picture is smoother, has no point where the physics breaks down, and makes predictions consistent with what the Planck satellite has observed. I know which one I consider more fundamental. And here is the part that should completely change the way you think about existence. The no-boundary proposal does not just resolve the singularity, it also provides a framework for understanding why the universe has the specific properties we observe. In quantum mechanics, you do not predict a single outcome, but calculate probabilities for every possible outcome. And when applied to cosmology through the sum over histories, the no-boundary proposal says the universe does not have a single history. It has every possible history, each weighted by its probability, and the histories that dominate, the most probable ones, are those that look like our universe, expanding, cooling, forming galaxies and stars and planets. In later work with my colleague Thomas Hertog, I pushed this even further, and we developed what we called top-down cosmology. The conventional approach in physics is bottom-up, where you specify the initial conditions of the universe and calculate what follows, but in a quantum theory of cosmology with no boundary, there are no initial conditions to specify. Hertog and I proposed that the direction of explanation should be reversed, and rather than asking how the initial state evolved to produce what we observe, we argued that the observations we make today select the relevant histories of the universe. The universe does not have a single history independent of the observer, and the act of cosmological observation plays a role in shaping what we can say about the past. This is not mysticism, but quantum mechanics taken seriously at the scale of the cosmos. The universe also appears to be extraordinarily fine-tuned for the existence of complex structures and, ultimately, life. If the rate of expansion 1 second after the Big Bang had been smaller by even 1 part in 10 billion billion, the universe would have recollapsed before it ever formed galaxies. A slight difference in the nuclear force would mean stars could not cook heavy elements, and if the electromagnetic force was slightly stronger, electrons could not orbit atoms in stable configurations. Changing almost any fundamental constant by a tiny fraction produces a universe of nothing, radiation, black holes, or formless gas, but nothing that could look back and wonder where it came from. What philosophers call the anthropic principle, the observation that the universe must be compatible with the conscious beings who observe it, is sometimes dismissed as a tautology. Of course, we observe a universe that permits our existence, because we could not observe one that does not. But combined with the no-boundary proposal and the sum over histories, this becomes something much more powerful. Out of all possible boundaryless histories of the universe, the most probable ones that contain observers look very much like the universe we see. The Big Bang, the expansion, the formation of galaxies, the forging of heavy elements in stellar furnaces, the assembly of those elements into planets and eventually into people who build telescopes and radio antennas and satellites, all of this emerges from the mathematics. Not from design, but from geometry and probability. For centuries, the question of why there is something rather than nothing belonged to philosophy and theology. What happened before creation? What caused the universe? What set it in motion? These seemed like questions science could never touch, But the no-boundary proposal moves the discussion squarely into the realm of physics. If the universe has no boundary, no edge, no point of creation, there is nothing for a creator to do, and no moment at which the universe needs to be set in motion. It carries its own explanation within its own geometry. I came to this conclusion not through philosophy, but through calculation, through applying the same mathematical tools that describe how electrons orbit atoms and how black holes radiate particles. The universe simply is. I should note, because I think it reveals something about how science actually works, that my own views changed over the course of my career. When I was young, I proved, with Penrose, that singularities were inevitable, that the universe must have a sharp beginning, a point where physics breaks. I spent the next 2 decades showing that this conclusion was premature, that when quantum effects are properly included, the singularity may dissolve into a smooth, boundaryless geometry. I proved myself wrong, or rather, I proved that the earlier result, while mathematically correct within its assumptions, rested on incomplete physics. That is not a failure of science, but science working exactly as it should. We are small creatures on a minor planet, circling an average star in the outer suburbs of one among 100 billion galaxies. The universe does not owe us simplicity or a narrative with a clean beginning, a middle, and a satisfying end. But when we apply the most powerful tools our minds have ever created, mathematics, physics, the relentless pressure of evidence and logic, we find that the universe is comprehensible, not simple, but comprehensible. And the shape of that comprehension is stranger and more magnificent than any story we might have invented. The universe is not a story that begins somewhere. It is a shape, closed, finite, boundaryless, requiring nothing beyond itself. We are brief, improbable patterns in that geometry, looking back at the whole of it for the first time and, against all odds, beginning to understand what it is. If we find the answer to that, why the universe bothers to exist at all, it would be the ultimate triumph of human reason, for then we would know the mind of God.